Hi everyone. Sorry for the delay because some emergency here today. Um, Welcome to 2023-2024 season USACO live solution session from XCamp. This is for the second contest just past last weekend. We are happy to have women here to provide the solution session. My name is Charlie. I'm the co-founder and the CEO of XCamp. Women is our kind of first group of students with XCamp, started from beginner. This year, last year, 2023, he got the honor to join the USACO, the summer camp, the national finalist. Also, I heard Wimo got early um, offer from MIT too. Today, we are very happy to have Wimo to help us uh, on a solution for this bronze contest. Wimo, turn back to you.
Oh, yes. Hello. Um, Give me a second. I have to having a little bit of difficulty setting up a whiteboard.
Okay. Yeah, let me stop the sharing now so you can share your screen. Yes, as I mentioned, Wimo joined us from the seventh grade, so he skipped a couple class. Also, he joined our summer camp in China, Hangzhou. So he kind of passed each level every year from the bronze, silver, gold, platinum. Uh, Also, finally, he got the chance to join the US camp. It's a long journey for him, but we can see this very successful story here. I know maybe not all of you will go through this long journey. Some of you might, learn some coding and then do other topics, for example, research, robotics, or AI, or other products. So anyway, hope you will enjoy the journey of learning coding and enjoy the journey to attend the USA contest and others.
Um,
Okay, yeah, we can see your screen now, Wimo.
Give me a second. Let's see. I draw on this. Technical difficulties. Oh, wait.
We can see your cursor. Yeah, we can see your mouse.
But it's not letting me draw. This is
You need to click the pen. Now you just click this. You need to click second one, the pen.
wait. Difficulties. Um, Sorry, I'm having a little bit of an issue. Wait, why? I don't know what I'm missing because don't see a, there's no, sorry. Uh, hmm, I don't know why it is. I can't.
Do you see the control panel on your left side? Do you think you can click the pen?
I don't see one, which,
How about you restart it? Yeah.
okay. Is it possible that you have to give me a permission to work on the whiteboard?
You are the co-host now. You should have the permission.
Because it was working last time at the very least. Oh,
How about now? Have a try.
okay. I just don't see something to edit it with. Um, sorry. Um, then I think it's a permissions issue because uh, let's try one last time. No, I don't know. I don't know exactly what's wrong here.
Let me give you try to give you the host. Okay. Yeah. You give me the co-host later. Yeah.
Okay.
Up to now.
Um, oh no, because I don't know why. I don't see a button to write with. Um, see if there's something else I can do instead. Okay. Wait, I'll try. I'll try something else instead. Oh, well, it works now. Okay, I don't know. I don't know what was wrong earlier. Sorry about that, everyone. Okay, this works. Sorry. So I guess I can get started with the problems then. So the first and then if you want the problem statements, I'll link a way to access those like in the chat later, I think. So the first problem is majority opinion. And the question basically asks if so you have an array of all right, you have you have an array A where A of I denotes the type of hay that cow I likes. And what you can do is in one operation, you can select a subarray from L to R. And within that subarray, if there is a type of hay that occurs as strictly the majority, or occurs strictly more than uh, L plus R over two times, then you can make all of the cows in that range like that particular type of hay. And the question is, for out, you have to output all the different types of hay such that after applying this operation a couple of times, you can apply it as many times as you want. You can make all of the cows in the array like this particular type of hay. For instance, one of the sample inputs is the array 1, 1, 1, 2, 2, 2. And for instance, in this array, if we select select our interval from uh, we select our interval from 1 to 5, we can choose this giant interval here, and we can make all the cows here. We can make all the cows in this range. So we picked 1 to 5. We can make all the cows in this range like hay type 1. And this is the result after applying the operation. And then if we select the entire array in our next operation, we can make every single cow like hay of type 1. And you can see that a similar thing is true, that you can make all the cows like hay type 2 as well. So so the first important thing that you can observe for this problem is that if you have two cows in a row, they can little by little, let's just say these are all two, and so on and so forth. if you have these two cows that are next to each other and they're the same type of hay, you can little by little force the entire array to be that particular type of hay. For instance, if you select your interval here, afterwards you now have three cows who all like this type of hay. And if you select or alternatively, you can select an interval here, and you'll have these four cows who like this type of hay. So in particular, if there's two cows in a row that like a type of hay, you can select a third cow on either end and convince the third cow to also like that particular type of hay. So this covers this covers most of the cases. And the final thing is that if you have a case that is like this, you can select this array and make all the cows like hay type 1. And then afterwards you now have two cows that are next to each other, who are next to each other who like the same type of hay. So you can convince the entire all of the cows to like this particular type of hay as well. So basically, if no, the final solution that you arrive at is that if A of I is equal to A of I plus 1, or A of I is equal to A of I plus 2, where this is the index, not the value itself, then you can eventually make all the cows like A of I. And then this is also the full solution. So what you can do is you can enumerate all of the A of I from 1 to n. And for each A of I, you check this condition. And if it works, then you mark this type of hay as valid. And then otherwise, you don't do anything with it. And at the very end, you can iterate over all the valid types of hay. So this can be done either using an STD set or just a regular array as well. And yeah, that should be the full solution. So just like as a recap, you notice that if you have two cows consecutive, or you have a cow that's in the you have two cows that are the same with one in the middle, then you can convince all the elements of the array to eventually be this particular type of hay. It's also worth mentioning that if this isn't true, it's always impossible. So, for instance, if we considered an array that looked like this, I'll use 2 instead of 0. 1, 2, 2, 1, and so on. It's never possible. So, since none of the ones are next to each other or spaced at most 1 from each other, it's impossible to make 1 have the majority of any subarray. Because, for instance, if we picked this, 1 isn't a strict majority, it's only split even, so this wouldn't change anything. And if we had picked this instead, the same issue arises, where 1 is only 2 out of the 4, where you actually need 3 to change the entire array. Yeah. And then that's the full solution for the first problem. I'll cover the third problem next, since the second problem is the hardest one in the set. Okay, so in the in the third problem, what you have is you can do two types of operation. We have operation of type 1, where you pick a number L, and what you do is you have actually, I should start off by defining some terms. So you start off with an array of length n, and your goal is to eventually turn all the elements in the array to 0. And to turn them all into 0, you have two types of operation. So in your first type of operation, you pick an integer L, and what you do is you have it's let me yeah, okay. So you have a of n minus L increases by 0, and then a of n minus L plus 1 increases by 1, and so on and so forth until you have a of n increases by L. And your second type of operation, which is type 2, is the same thing, but instead of increasing, you're decreasing. So here you have a of n minus L minus equals 0, and a of n minus L plus 1 minus is equal to 1, and so on and so forth. And the question is, what is the minimum number of operations in total of both types combined you need to apply to eventually turn all the array elements into 0? So to solve this problem, we need to observe a couple of things. So I'm gonna erase this. To Jaden, this is the second problem, or this is the third problem. Yeah. So the first thing you notice that is it's never optimal to do an operation of type 1 for a certain L and then do it for type 2 for a certain L, because the two operations would cancel out and you would have done two operations for nothing, and would have been more optimal to just not have done anything at all. So that's the first important observation. And the second important observation is that no, we're currently on problem 3. The second important observation is that if you consider the first element in the array, I don't know what happened just now. If you consider a of 1, you can only ever use operations with L is equal to n minus 1 to update array of 1, because all the other operations stop too short. For instance, let me again. If you set L to be equal to, you set, yeah. Oh no, actually, sorry. If you set L to be, I got one of the definitions mixed up earlier. If you set L to be oh sure. I should send the statements. Give me a second. Um Let me see if this works. Oh, okay. Cool. Okay. I sent 3 images in the Zoom chat, each corresponding to the problem statement of that particular problem. And then we're currently on problem 3. What I said earlier was wrong. I got L and I got the definition of an operation confused. It's that you have like sorry. If you have an operation of type so like an operation of type L has an array of n minus L plus 1. No, actually, no, I didn't get it wrong. Yeah, plus equals to 1, and then array of n minus L plus 2 plus equals to 2, and so on. So anyway, what you can what you can notice is that, first off, the only type of operation that can affect array of 1 is the type of operation when L is equal to n. This is true because if you set L to be anything lower than n, say you picked n minus 3 or something, you actually won't change array of 1, because you'll only ever change the furthest left, the smallest element, the smallest index you will change is equal to n minus L plus 1. And you have to set L to be L equals to n in order to edit the first number in the array. So what this leads so what this means is that the number of operations of type L equals to n is actually, or like, you know that will, so say array of 1 is greater than 0. In the event that it's great, or I should say less than 0, that'd make more sense. In the event that array of 1 is less than 0, we need exactly array of 1 operations of type 2, or type 1. Yeah, operations of type 1 to make array of 1 equal to 0. Because in each operation, we are setting, well, in each operation, we're going to increase the value of array of 1 by 1. So after applying exactly a of 1 operations, you would have set a of 1 equals to 0. And then in the second case, where a of 1 is greater than 0, then you also need exactly a of 1 operations of type 2. And it's the same logic. And in particular, you can't do it in less than a of 1 operations, because if you use less than a of 1 operations, you wouldn't have actually changed the value at all. And you also don't need more than a of 1 operations, because earlier we demonstrated that there's no need to use more than one operation, more than one different. There's no need to use a type 1 or a type 2 operation at the same time for fixed L, because they cancel each other. So we know that we need to use exactly a of 1 operations of type L. So now that we know that, let's say we applied all these operations to the array. So after we applied all these operations to the array, we now have a of 1 is equal to 0. And actually, we can solve the exact same problem again for a of 2, because the same logic still applies. You only operations of type L is equal to m minus 1 can change array of 2. And basically, this logic, by using this logic, you can set the numbers from 1 all the way to n in increasing order. You set them to 0 one at a time, and each time you know exactly what type of operation you want to use. So the only tricky part now is how we can effectively simulate how we can effectively simulate applying all the operations, because after trying each L, we can't actually update the array directly. That would result in an n-squared algorithm, which would TLE. So, so what is needed is that we have to. So what is needed is that we have to simulate this in a smart manner, and the way we can simulate it well is that, so say we know that we used. So say that we know that we used here. Okay, if we used, sorry, my pen is having issues right now. So if we used X operations of type 1, we use X operations of type 1, and then we used Y of type 2. And then in addition to that, we also store the sum of all the operations that we've like done so far, which would be how do I put this? Yeah. So, okay, if we store the total sum of the effects of all the operations we've done so far, let's keep that in a value called sum. So basically, every single time we apply an operation of type 1, sum will increase. And every single time we apply an operation of type 2, sum will decrease. And the important thing is that when you consider the effect of all the if you consider the effect of all the operations on array of I, and you think about the effects of operations of array of I plus 1, they're actually really similar, right? Because all the operations would have added some value x to I, and then they would have added some other value x plus 1 or subtracted x plus 1 from I plus 1. So when you move from I to I plus 1, if you know the amount of operations of type 1 you've done, you actually just have to increase sum by x because that corresponds to taking every single operation of type 1 you've done so far and shifting all of their values of x to be x plus 1. And the same logic is true for y, which is that if you take all of the operations of type 2 you've done, it's the same as when you move from I to I plus 1, it's the same as if you just subtracted y, since you would have taken all the negative x's and changed them into negative x minus 1, or here negative x plus 1. And this is the same thing as because used y updates of type 2, you would have changed each one of them by -1, which is subtracting it by y. So by using this clever trick, you can actually simulate the effects of all of the operations you've done so far and effectively compute how they change as you shift from one element to another. And the final thing is that in the problem, at the very end of the statement, they say it is guaranteed that the answer is at most 10 to the ninth. This doesn't seem like a very useful fact, but actually, by guaranteeing this fact, your code won't overflow a long as you run this process, because otherwise you would end up with really large numbers, but luckily for us, they guarantee that that won't happen. So that's the full solution for problem 3. I think it would probably be good if I sent code for that. So I think after I finish presenting all the solutions, I'll send like a link containing the solution codes for all of them. Okay, and then finally, I'm gonna go over problem 2, which is, I think, without a doubt, the hardest problem in the set. So for problem 2, so Bessie is jumping on a number line, and she has two types of and on her number line there are jump pads and there are targets, and for each target there's a value v, where if Bessie's current velocity is greater than or equal to v, she will break the target. And on each jump pad, Bessie, there's a value. I forgot what they said it was. It's just the v. Bessie will increase her velocity by v, and then she'll reverse her direction. And then Bessie the cow initially starts so Bessie the cow initially is at, oh yeah, and then when her velocity is v, she will move forward v steps in a particular direction. For instance, if Bessie the cow is currently on position 1, my pen is broken again. Okay, if Bessie the cow is currently on position 1 with a velocity of 2 and she is facing to the right, uh, then after one jump, she's going to end up at position 3. Or she will increase, oh, what happens now? She'll increase her velocity, or she'll increase her position by the amount of her velocity in a specific direction. And then say at position 3, her velocity somehow changed to be 3, and she also switched directions. And now she is facing to the left. She would now jump to 0, which would be 3 minus 3. So Yeah. Okay, so so Bessie the cow starts off initially at she's initially at position S with a velocity of 1 and then facing the right. Facing right. And the question is, after some indefinite amount of time, what is the total number of targets Bessie the cow will break? So there's a couple ways to think about this problem, but the most basic is to just imagine simulating the process where you keep track of Bessie's position, her velocity, and her direction. And you just simulate this process some amount of time, for like, I don't know, just for a while. And so there's a couple of important things. The first thing is that if Bessie the cow ever ends up at the same position, velocity, and direction that she has already been at before, she will end up in a loop forever. And this makes sense because if Bessie is currently at some state, my pen is broken. Oh, I don't know why Okay, if Bessie the cow is currently at some state, right, she'll move forward to another state. But if she ever finds her way back to the same state of having the same position, velocity, and direction, she's stuck in a loop because she'll move forward again, and eventually she'll make her way back. So, so if she ever ends up at the same position, velocity, or direction, Bessie the cow cannot break any more targets because she would have broken everything already, and now she's stuck in the same loop forever. Similarly, if Bessie's position is ever less than 1 or greater than n, she also will no longer break any more targets because once she's past the interval where from 1 to n where there exists jump pads, she'll never change her direction. And if she ever goes past 1, her direction has to be facing the left, and she'll have to bounce off towards negative infinity forever. And the same is true if she ever ends up at a position strictly greater than n. So now we know when to terminate. And now the question is, what's the maximum number of states Bessie can be in? Where state is defined as position, velocity, and direction. How many states can Bessie the cow be in? Because if she can be because preemptively, it looks like she could be in n squared states, where her position is everything from 1 to n, and her velocity is everything from 1 to n, and also 2 directions. But And if this is the case, then this algorithm will actually be too slow. But I'm going to show that this is actually not the case. And Bessie actually is in at most um, O of n log n states. So, okay. And then I'm going to erase some of the other stuff. And the rough idea of the solution is this. So let's say Bessie has her velocity currently equal to v. And she's facing some direction. Let's just say she's all right. Yeah, so she has a fixed velocity and a fixed direction. Uh, um, my pen is having a seizure. Okay, she has a fixed velocity and a fixed direction. And I claim that Bessie can be in at most n over v states with the n over v positions with this velocity in this direction. And this is how it works. So first off, note that if Bessie the cow ever switches her direction, her velocity will end up strictly greater than what it was initially. And this is true because to switch direction, she has to land on a jump pad. And if she lands on a jump pad, her velocity will increase. Wait. No, 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 no. Sorry. Let me take that back. All right. Yes, that was not what I meant to say. All right, so I forgot that the value could be zero. Yeah. All right, so Bessie the cow for fixed velocity and fixed direction. So first off, her velocity is it's non-decreasing. Yeah. It can't end up at some value strictly less than what it was initially because her velocity will only ever increase or stay the same, right? And what this means is that Bessie the cow is going to jump forward v uh here, and then jump forward v again, and so on and so forth, until eventually her next jump will have to exceed n. Or it'll be yeah, or her next jump will eventually have to exceed n, or similarly, it'll eventually have to be less than one. And basically, she can't she can only visit these particular jumps that are of size that are of distance v from where she is currently, and she can't really shift between that because she can jump yeah so let's I don't know how it's like yes you can jump between different indices that have like the same value mod v, but she can't actually change her value mod that particular v because to do so she'd have to increase her velocity. And changing the direction, she'll still end up in the same set of indices, and there's at most n over v of them. So so you can show that for fixed v, Bessie can be in no more than O of n over v states, n over v positions. And when you sum this up over all the v, you end up with a sum that looks like this. It's like sum of sum of n over v, v goes from 1 to n. And if you know where this is going, it's that this sum is actually it's called the harmonic sequence. And this is the same thing as if you have n equals 1, 2. So you extract the n of 1 over v. And it's a well-known fact that the sum of all of the fractions or like reciprocals from 1 to n is approximately log n. The proof for this, I guess you can Google it, and there's another pretty nice way to do it by grouping powers of 2. But this sum is log n. So the result is that Bessie the cow can be in O of n log n different states. And what this means is that we can actually just simulate the process until she either visits the same state twice or jumps off the map. Or jumps off the map in the sense of like having a position less than 1 or greater than n. So what we can do is Silver should start in a couple of minutes. So what we can do is we can keep of an STD set where we store our current direction, position, and velocity. And all right, yeah. My pen had to see here again. Here we can store a set of all the directions, positions, and velocities we visited so far. And if we ever visit the same state twice, we can break immediately. Otherwise, we simulate what happens at that step. So we will either update our velocity with the current we'll either update if we land on a jump pad, we'll change our velocity and direction and position afterwards. And if we land on a target, we'll check whether or not the target has been broken. And if not, we'll see if we can break that particular target. And the n complexity will end up being O of n log squared n. Oops, squared n. Yeah. And that's the solution for bronze P2. Yeah, that would be all. Are there any other questions? And then I'll send the code for the problems in a second. Okay, then thanks for attending. Give me a second to stop. And sorry about all the issues with the whiteboard earlier. Think I must have clicked a wrong button or something.
Thank you, Wilmo. Yes, we have a quick summary about the questions. Let me show you. Yeah, Wilmo, here's the quick summary. Maybe you
Yeah.
can give a summary now.
So the first problem is greedy or a simulation, depending on how you see it. And then the second problem is most definitely simulation and also a map or set or something to efficiently check whether or not you've been in the same state multiple times. And the third problem is math and sweep line, which is, a fancy way of saying a for loop. Because as you consider each element in the array individually, it's the same as if you had if you were sweeping on it. And it's also a simulation depending on how you see it. Yeah.
Okay, yeah, thank you, Wimo, for your time. Also here, we have a service to provide a USACO report card. Please visit our website, xcamp.academy/. You will find there's USACO report card. Then you post your test cases. So our teacher will send you a detailed report and estimate the score within 12 hours. So from here, you can have a very good diagnosis on your results, and we may provide you further advices on your USACO journey. Yeah, please access our website and submit your result and get our USCO report. Okay, that's all for this solution session. We have several questions, I think, here. Wimo, do you check the chat?
Uh, yeah, I think I answered all the problems prior to the one Peter just asked.
Oh,
Um, I think I don't know about cutoffs for this contest. I think that like I'm not like officially connected with USACO or anything, so I can only make speculations. But yeah, I agree this contest was a bit easier than usual. And I think that seeing a cutoff that's uh seeing a cutoff that's like 750 to 800 is very likely. Cutoffs for the contest never are like they're rarely ever higher than 800 or strictly higher than 800. The only time they set an 850 cutoff was a one-off situation where you can guess 50% of the test data. So yeah, the cutoffs generally are less than or equal to 800. And yeah, this contest was a little bit easier than usual.
okay, great. Yeah, thank you, Wimo. Again, here we have XCamp classes. We provide the opportunity for you to continue learning and improve. We have a year-round weekend class. It's a 4 quarter a year, 10 week for each quarter. Also, we have on-site camps. We have a summer camp and a winter camp. It's in the Bay Area. For the winter camp is 1 week, 5 days. For the summer camp is 2 weeks from the end of July. This year is July 22nd to August 2nd. Also, we have mock tests. So to practice to get a good score, you can join our mock test. We also have grand master classes. That's for later on when you're in the gold level and the platinum level. If you're also taking APCS class, if you need help, you can join our APCS class too. Okay, that's all for this live solution for the USACO Bronze 2023 to 2024 season, the second contest. Thank you all. Also, thank you, Wimo, again. Also, I'm very sorry again for the technical issues today. Okay, great. Have a nice week. I hope you got a good result. If not, it's okay. This is a learning journey. Hope you can do better next time, especially after this solution session. Okay, thank you all. See you later. Wilma, would you give me the host?
All right. I just changed it.
Okay. Okay.